Okay, thank you, Yang Yang, for the introduction, and thank you for attending this talk. Okay, so today I'm going to talk about my group's recent research on deep learning, in particular deep AUC maximization, and its application in medical image classification. And so I hope to convince you that this is an interesting problem. And I also found there are many interesting open mathematical problems and also some engineering problems there. Okay, so this is outline. First, I will give you an introduction. And then we talk about our proposed new surrogate laws for the AUC. And then talk about optimization algorithms for learning deep neural network by maximizing the AUC score. And finally, show you some evaluation results, experimental results on medical image classification tasks. All right, so we know that deep learning is everywhere, right? So compared to traditional machine learning approach, deep learning is able to learn the feature in an end-to-end fashion, right? So it works very well for image data, for speech data, for natural language data, right? Right, so we have heard a lot of great stories, right? So image recognition can beat human performance, right? AlphaGo can beat human champion, right? So many great stories. But is deep learning power enough? Is deep learning trusty in everywhere? Actually, the answer is not yet, right? So we have seen some stories, some news like this, right? So Google Photos, right? So app of Google, Google phone, right? So there is app Google Photo, right? So it labeled black people as gorillas, right? It's definitely not good, right? So another news, CNN news here, sorry kids, Apple's new Face ID isn't mean for you, right? So Google, you see that Google, Apple are giant players of AI. They have many money, right? They have many talented people in AI, in machine learning, right? But still there are some problems there, right? So what's wrong? Right? So what's wrong with these AI systems, right? So when you want to understand this problem, I want to, introduce you like three key components of machine learning. Right? We want to understand problems from the perspective of machine learning, right? So the three key components. So the first component, of course, is data, because machine learning data, deep learning is data driven. Right? So you have to understand your data, okay? So that is the first component, data. The second component is modeling. Right? It's how you model your data, how you formulate your objective, right? And the third step, the final step, is optimization. Right? It's how do you optimize your objective to find a good model. Right? A good model not only for your training data, but also good for the new data, for the testing data, right? Okay, so let's first look at the first component, data. What's wrong? What's wrong with the data component in those bad stories? Okay, actually, what I envision that problem is that there is imbalanced data problem, right? What does it mean? Right, so if you have, for example, two class classification problem, right? So there is one class could be with very few examples, right? In the Apple Face ID case, right? So the example, the images for kids is much less than the images for adults, right? So that's the data imbalance. And similarly for the Google photo case, right? So the images for black people will be much less than the images for the white people. Okay, so that's the data imbalance problem. And this is very widely, it's a very common problem, okay? Not only in those applications, but also in many other applications. For example, in medical domain, you want to detect certain rare diseases, right? So the patients with that disease will be very few. Right? So there are many examples have this data imbalance problem, okay? So if you just take a standard approach to minimize the average training error, you may end up with a bad model, okay? The bad model cannot perform well on the minority data. Right? So that's the problem happening in the Google Photo in the Apple Face ID cases. Okay, so second component is modeling, right? So right now you have an imbalanced data. You want to rethink how to model the data, okay? Another way is how do you formulate the objective? How do you measure your classifier's performance? Okay, so in the literature, there are several measures, right? So the standard measure is called accuracy, or the error rate, right, which is 1 minus accuracy, which is out of all the examples, how many of them are predicted correctly, right? But this is not suitable for imbalanced data. Right? Imagine you have a data with 99% of data to be negative and only 1% to be positive, right? So if you have a model predict all the data to be negative, right? So you have 99% accuracy, right? But that model is not useful. Okay, so the accuracy measure is not good for imbalanced data, right? So there are some other measures for imbalanced data, right? So for example, F measure. Okay, F measure is often used in information retrieval, in search, right? In search, in Google search, right? So today I'm going to talk about another measure. It's called the area under the ROC curve. I believe you have heard this measure, right? It is widely used in medical analytics, right? Medical analytics. So what is the ROC curve, right? So ROC curve is the curve, right, of the true positive rate versus false positive rate. So basically, if you train a classifier, right, so the classifier usually output a score given the data, okay? And then you can define a threshold. Above the threshold, you classify the data as positive. Below the threshold, you classify the data as negative, okay? And then you can change your threshold. By changing the threshold, you can plot different points of true positive rate and false positive rate. And then you can get a curve. That is the ROC curve. All right. So if you have a random guess, your classifier is just random guess, and then your ROC curve is just this diagonal line. And of course, you want the classifier to be much better than this random guess, right? So you want the curve to be as high as possible, so that the area under the curve is as large as possible. Right? So that is the area under the ROC curve, right? Right. So it has a long history. It was first introduced in the World War II for measuring the ability of a radar receiver operator, and nowadays widely used in medicine, radiology, biometrics, epidemiology, etc. For the diagnostic analysis, right? For evaluating, for comparing the classifiers, right? Okay. Right, so why don't we optimize this AUC directly, right? Okay, so this is another definition of AUC, right? So previously we've seen the AUC is the area under the curve, but it's not very good for optimization, right? So for optimization, we want to find a differentiable function, right? So we can compute a gradient, we can optimize. Okay, let's look at another definition of AUC. So this is the AUC defined on the population level. Okay, so given H is your classifier, is your model, prediction model. And this true AUC of this classifier is defined as probability the score of a positive data or random positive data is larger than the score of a random negative data, X prime. Okay, so the Y equal to 1 is the label of X, Y prime equal to negative 1 is the label of X prime. Okay, so basically as X is positive data, X prime is negative data. All right, so this is also equivalent so-called the Wilson statistics. All right, and because this definition, right, so it compares all the pairs, positive and negative data pairs, so it is very suitable for imbalanced data. Right, so it will not suffer from this issue of the traditional accuracy measure. Okay, and here we are interested in learning a deep model, right, a deep neural network to implement this predictive model edge. Right. So the problem will be a deep AUC maximization problem. All right, so that is the background. All right. Okay, so next let's look at how do we maximize AUC. Okay, so the first thing is we need to find a surrogate loss, right? So the original definition. So by the way, if you have any questions, you can interrupt me. You can just ask me the question. It's okay. Okay. All right. So the original definition we have seen there is the probability of the prediction score of a positive data higher than the prediction score of a negative data. We can also write in this way is the expectation over the data random data x prime. This I is the, you can consider is a 0, 1 loss, right? Or the indicator function, actually is indicator function, but in machine learning, we can call it 0, 1 loss. That means that when the hx larger than hx prime, you have a 0 loss. You are good, right? When hx is less than hx prime, you will have a loss equal to 1. Right? So that is a 0, 1 loss. Okay, a 0, 1 loss is not continuous, not differentiable, it's not good for optimization, right? So usually in machine learning, we want to find some surrogate loss, right? To approximate to, right, the 0, 1 loss, right? So you can choose a surrogate loss, usually convex surrogate loss, L function here, right, to replace the 0, 1 loss, and then you want to optimize this objective, right? So surrogates of the AUC to find optimal classifier, right? So in the literature, there are many surrogate loss has been proposed for this indicator function, right? For the 0, 1 loss, for example, the Hengel loss, right? So Hengel loss is this green curve, like in green curve, and the square loss is this red curve, right? Okay. All right, but there is a problem, right? So there is a problem of optimizing this pairwise surrogate loss for AUC. Pairwise means that each loss value here, right, involves a pair of positive data and of negative data, right? Okay, so there are some issues there. So first, if you optimize this, it will give you high computation cost at each iteration, and also at the whole level. So for example, each iteration, if you sample big examples, you want to construct the pairs between the big examples, right, to compute gradient, stochastic gradient of this objective. And so that will be B square complexity. Right? So if you have a total of n examples, so the complexity could be as worse as n squared. And so that is quadratic. And that is not good. Okay. The second issue is that this pairwise loss is not suitable for online learning. So in online learning, data is coming sequentially, right? Data is coming sequentially, right? So maybe today you receive a positive data, and tomorrow you receive a negative data, right? But in online learning, you want to update the model once you receive some data, so that you can perform better in the future. All right. So in this setting, right? So if you only received one data, how do you construct pairs? How do you compute the stochastic gradient, right? Right. So one solution you may want to wait for a few days to receive more data and then construct pairs. But maybe the scenario is very unlucky, right? So in several days, all the data you received is negative, right? And how do you do that? And so it's not suitable for online learning. And it's also not suitable for distributed optimization. In the distributed optimization, data are collected at different size. You cannot share the data, you cannot move the data. But you want to optimize this objective in this distributed fashion. Right? So if this is pairwise loss, you want to construct pairs between the data at different machines. So this will involve a lot of communication. Right? That's not bad. That's not good. That's not good for distributed optimization. Okay, so there are many challenges here for optimizing a pairwise surrogate loss, a general surrogate loss for AUC. Okay, so in 2011, we are actually the first group to consider this online AUC maximization problem. Right. So what do we propose? We propose a buffer, a data buffer. We maintain some positive data, representative positive data, some representative negative data. And when new data is coming, we construct pairs between the new data and data in the buffer, and to compute approximate AUCs. Okay, but the problem is that we actually prove that this buffer needs to be very large in order to make the algorithm work very well. So it cannot scale up. Okay, it cannot scale. All right, so that's a problem. Okay, all right. So there's a problem of pairwise surrogate loss, but there is an exception. Okay, there is an exception. Square loss is an exception. Okay, square loss. What is square loss? Right. So square loss here is that you compute the difference between the score. So here I use HW to denote a prediction score, and W is the parameter of the function to be learned. For example, the weight of the neural network. Okay. The square loss here, this is the difference between hx and hx prime and minus the target one. Right? So basically you want this difference to be 1. And so that's square loss. Right? That's a square loss. Okay. Okay, square loss, there is a benefit. So in this paper, in et al. In 2016, they found that this pairwise loss can be written as a min-max formulation. Okay, and the good thing is that right now the objective F is expectation over the individual data Z. Right, so Z is the data includes input X and output Y. Okay, so right now you can actually decompose your objective over individual examples. You don't need to construct pairs. Right? The only difficulty is that right now you have a min-max problem. A min-max problem has been studied a lot in the literature. So basically, you can use a stochastic gradient descent type algorithm to solve this. Right? Every iteration, you can sample one data to compute to update your model. So this is very good, very nice reformulation of the square loss. In et al. Focus on linear model. Okay, only focus on the optimization perspective. But square loss good enough for AUC maximization? Right? Not really. Right? So actually, we found that square loss is not good. It's actually not good for AUC maximization. Okay. There are 2 issues for the square loss. First is that it has an adverse effects on easy data. So when you train with the easy data means that it's well classified. Right, so for positive example, its score is very large. For negative example, its prediction score is already very, very small. Okay, easy data. Okay, with this easy data, actually you will see that the square loss still gives you loss. Right, the model is good enough. Right, so the prediction on the positive data is large. Prediction on negative example is small. Right, it's already a good model. But if this difference is large, very large, and it's not equal to 1, you still have the loss. That's not good, right? If you still have the loss, and then if you take gradient of the loss, you will drive your model to the wrong direction. Right? So that is the problem, one problem of square loss. Right? So here we on toy example showing that. So this is pre-trained. So on this data, we pre-train the model like this, and then when you add some easy examples, okay, and then you can keep optimizing your square loss for the AUC, and your model, your decision boundary become worse. Right? So that is the first issue of the square loss. Second issue is that it's very sensitive to the noise data. Right? So that is actually a common problem of the square function, the square loss function. Okay, so this is when you add some noise example. So this blue circle is noise example. Your model will be also updated to the wrong direction. Right, so there are 2 issues of square loss. Square loss is good for optimization, for stochastic optimization for big data, right? Because we can decompose the pairwise into individual examples of expectation over individual examples. But it's not good for generalization. Okay, so we propose a new loss we call the margin-based surrogate loss. Okay, so this is what we do. So first we decompose the square loss, okay, the square loss into 3 components, and you will understand these 3 components, very intuitively, and then you will see the problem, and then you can, improve that. Okay, there are 3 components. All right. So the first component here is actually the variance of the score, prediction score of the positive data. Right, so the HWX minus AW. AW here is the average score of the positive data. Right, so this is the variance of the prediction score on the positive data. And this second term is the variance of the prediction score on the negative data. Right. So minimizing this loss means that you want the prediction score of the positive data and also prediction score of the negative data to be concentrated. Right. So that's the first 2 components. The third component is trying to, so this is 1 plus BW minus AW. So basically you want, so So the goal is actually you want AW to be far away from BW, or to be larger than AW is a prediction score, average prediction score, a positive example, and BW is the average score of the negative data. So basically, the certain you want this AW to be larger than BW as much as possible, right? Okay, but the square loss is a problem here. Okay, square loss is a problem here. So that gives you two issues that I mentioned before. Okay, to address this issue, I'm going to replace this function, the third component here, only the third component here, because the first two components are very intuitive. Okay, you want to minimize variance of positive data and variance of the prediction score of the negative data. Okay, there is no problem of those two terms here. And so the problem is the third term here. So we replace this square function by a margin-based loss function. So basically, we replace this function by a Hengel. This is the Hengel function and square. Also introduce a parameter m on a margin parameter to make it more robust to noise data. Okay, so basically we have two changes here. First is we have the Hengel function here. Hengel function is defined here. We only take the positive component, meaning that I want AW to be larger than BW with a margin m. If it is larger than BW with a margin m, we are fine. If not, there is a loss. Right? If it is larger than certain margin, we are good enough. There is no loss. Okay, so there is a Hengel loss. Right? And another change is this margin parameter to make it more less sensitive to the noise data. Okay, so this margin-based surrogate loss is more robust than the square loss. So here we have the same toy data. You see that we add the same set of easy example, so the new loss give more robust solution. And similarly for this adding the noise examples, okay, so the solution of optimizing the new surrogate loss is much better than the square loss. All right, so this is a better surrogate loss for AUC. Okay, is there any question? All right, so let's move on. So next I'm going to talk about how to optimize this surrogate loss. All right. So we talk about the objective, right? So next is how to optimize this objective, right? To train your deep neural network, right? To learn this deep learning model. Okay. So the benefit of margin-based surrogate loss is that it can enjoy the same benefit of the square loss for stochastic optimization for big data. Okay. So we have the three terms, right? So first two terms is the same as the square loss. The last term, we can use a convex conjugate to write that into the maximization over or dual variable after. Okay, so basically this component can be replaced by this maximization component. So this m plus b minus a can be replaced here, and then you can also, so here what we do is we also let a and b to be a variable to be minimized, right? And then we end up with a min-max problem, right? So this is very similar to the min-max problem of square loss. The only difference here is that we have a constraint on alpha. Okay, we have a constraint on alpha. Okay, so if you want to learn, so here I didn't show the particular form of this objective function. But if you want to learn a deep neural network, so this objective function is going to be non-convex in terms WAB, and it's going to be strongly concave because there is a quadratic function on alpha here. So it's strongly concave in terms of alpha. Okay, and it's a min-max problem. All right. Okay, so next I'm going to consider how to optimize this min-max problem. Okay, so min-max problem has been studied on a lot.
Can I ask a quick question for your previous slide?
Okay.
So for your A1W, that formula, so basically you want to minimize A1, right?
You want to minimize A1W, yes.
Yeah. And if you have this formula, it seems like you can calculate stochastic gradient, right? So my question is, what's the motivation, say, to reformulate into the min-max problem?
Okay, so All right. So when you do that, right? So the AW here actually is an expectation function over your data. Okay, and BW is the same thing here. And here, this is also you can view this as compositional problem.
Mm-hmm.
The function of another stochastic function. So basically, for this type of problem, you cannot compute a unbiased stochastic gradient. But of course, there are some other techniques you can use, but that techniques usually require the outer function. If you consider this the compositional function, they require outer function to be smooth and Lipschitz continuous.
Okay, so you are saying the A function, B function is some composition of the expectation function.
Yes, yes.
Okay.
So AW is actually expectation of HWX given Y equal to 1.
Okay, but then in the min-max problem, it looks like it maybe still have the composition term, do you?
So in the min-max problem, first we make A, B to be free variable. So it turns out if you minimize over A will be the mean value. If you minimize over B, B will be the mean value of the negative score, right? So that is how we handle these two terms here, AW and BW, to make it free variable. For this BW, AW here, we just leave it as a stochastic function because right now is a linear function in terms. So if I put this over the S here, right? So it's a bilinear function in terms of dual variable alpha, and it's a stochastic function in terms of W. That's fine. We can compute stochastic gradients.
Yeah, maybe I missed something because you don't have the formula of the capital F.
Yeah, I didn't have formula. I don't want to overwhelm the reader. Usually, I don't want to do that. But basically, this term you can just replace this S by this term, and the BW is the expectation of HWX.
Okay, so in your max part, that A and B are still the expectation.
So the W part is still their expectation over the data, random data.
Right. I mean, so you replace the positive square term, right? So in that part, it's basically your S is the A and B part, right?
Yes, S is M plus BW minus AW. Right now, we consider BW, AW as the expectation, the random stochastic function.
Yes, so in your capital F, you still keep A and B as a function of W, or
so the AB here, this A and B is a free variable is replacing this AW and BW. And for these two parts, we just use the stochastic function.
Oh, I see. Okay. So yeah, A and B just replaces the first two terms, but for the third term, you still keep the function.
Yes.
Okay,
yes.
I see.
If there is no AB here, if I minimize A over this term, then A is the right thing we want to get.
I see. I thought you place all places of A and B.
No. Yeah. Yeah, that's a good question.
Okay, got that. Thank you.
Okay, yeah. All right, so as I said, min-max optimization has been considered a lot in the literature, right? So and there is a stochastic method like stochastic gradient descent, a very popular method. So, but right now you have primal variable and dual variable, so you take the stochastic primal dual method, right? So basically, what you do is on the primal variable part, W part, you compute the stochastic gradient, and then you take the stochastic gradient descent. Okay, and the dual variable part, you take the compute stochastic gradient, and then you take the stochastic gradient ascent. Okay, so here this operator means the projection this solution into the domain if you have a domain. Okay, if you have a domain. So here for the alpha we have the non-negative domain, so we need to project the solution into the non-negative domain. All right. And so this is the stochastic primal dual method, and after capital T iteration, you can return the last solution, you can return the average solution. Okay, so this is the stochastic primal dual method. It's very easy. It can be scaled up to big data, right? But the problem is that the previous studies are focused on the convex concave problems. Also, all the analysis, okay, most of the analysis, okay, are for the convex concave problems. Assume the function is convex in terms of W, in terms of the primal value. But which is not the case for our problem, right? For deep learning problem, it's non-convex, okay? Okay, so I'm going to design some new algorithms, right? But turns out that we still want to leverage the existing algorithms for solving the convex concave problems. Okay, so here we consider a family of, actually this family is broad enough to cover our problems. So this family is called weakly convex and strongly concave problems. Weakly convex means that if we add a quadratic function over the due of the primal variable w, the objective becomes convex. Okay, so original function fw alpha is non-convex in w. If we add a quadratic function, it becomes convex. Then we call it weakly convex. Okay, right. So if your function is smooth in terms of w, then it's definitely weakly convex. All right, and then we're going to based on this property, we're going to solve this problem by the famous proximal point framing. So basically, we're going to add a quadratic function w at the case stage. Okay, so we run the algorithm in multiple stage. At the case stage, I'm going to add the quadratic function w minus wk to the original function. Right now, to make the function strongly convex and strongly concave. Okay, and then you can use previous algorithm, right, to approximately solve this. You don't need to solve to get optimal solution. You don't need to do that. You just get approximate solution wk plus 1, alpha k plus 1, and then iterate this process. Okay, so this is the algorithm here, is what we call stage-wise stochastic primal dual method. So it runs multiple stages. Every stage, you add a quadratic function, w minus the cavernous solution w, and then use stochastic primal dual method to optimize this function, starting from cavernous solution w, cavernous solution alpha, with a constant step size, okay, with a number of iteration ts. So the eta s is the step size that I forgot to mention here. So that is the eta here, which is the eta here, the step size. Okay, right. So each stage, okay, we use a constant step size eta, indexed by the s with a stage number, and run a number of iteration ts. Okay, and this is how we change this eta, the step size, and ts. Okay, so after each stage, I'm going to decrease the step size, and I'm going to increase the number of iterations for each stage. Right, so the step size is decreased in a stage-wise manner. Okay, and finally we return the last solution of the primal variable dual variable. Okay, so this is stage-wise SBD. And in our recent NIPS paper, we proved that this algorithm, right, can enjoy one over epsilon 4 complexity for finding an epsilon stationary point if the function is smooth. If the function is non-smooth, is a epsilon nearly stationary point. Okay, all right. And it turns out this complexity is the optimal complexity that matches the lower bounds in this paper. So actually, our paper was first, published online last year, but it was accepted in this year's NIPS. All right. Okay, so analysis of this algorithm involves duality gap of the regularized function. So I'm not going to talk about that. All right. So we also recently get an improved rate, right? So because in practice, your problem or your deep learning problem usually has some nice problem. Okay, so there is one problem called the Polyak-Louis-Schwarz condition, or PL condition. Okay, so basically, if you consider the primal objective, okay, by maximizing over the alpha, you get a primal objective, right? So if the gradient of the primal objective at any solution W is larger or equal than the objective gap between PW and optimal solution, right, multiplied by our constant mu, and then this function is called to satisfy the PL condition. Okay, so this condition actually means that if you have a stationary point, you actually have the global optimal solution, and also it's very similar to the strong convex condition, but it's kind of weaker, much weaker. Okay, in this paper, Alan Juice et al.'s paper, they proved that, okay, for an oval parameterized neural network, okay, you can actually have this PL condition. What they prove is that, so around random initial solution, right? So there's a neighborhood you always have a global optimal solution. And in that neighborhood, there is a PL condition. Okay? Okay, so for us, what we do is we simply assume this PL condition holds in the globally, and we try to design more faster algorithm in practice. Okay, so this is a new algorithm under the PL condition. So it's very similar to the first algorithm I showed, but the only difference is that right now you change your step size quickly. Okay, so after each stage, your decrease step size exponentially by a constant factor. Okay, similarly increase your number of iterations exponentially. Okay, so that your number of stages is only a few number of stages you can stop your algorithm. But in the first algorithm that I showed that you need a large number of stages in theory. Okay, so here what we show is that this algorithm under the PL condition can enjoy this complexity whenever mu square epsilon for finding an epsilon optimal solution. Epsilon optimal solution means that the objective value of the primal objective minus optimal primal objective value is less than epsilon. Okay, and this complexity in terms of epsilon is also optimal, but the dependence on mu, the mu square dependence is definitely not optimal. But actually, we can also make it optimal. So we can replace this SPD algorithm, as I said, right? So this new function is strongly convex, strongly concave. You can use all the existing algorithms, proposed for strongly convex, strongly concave. You can put it here. Okay, basically you can put it here. So here we can also use, for example, other algorithms like stochastic extra gradient algorithm, AdaGrad, variance reduced algorithm, right? To improve the complexity, right? So if you use a variance reduced algorithm, you can make the mu squared to be mu. You can get the optimal complexity. Okay. All right, so that is the stochastic algorithm, okay, for solving this deep AUC problem. So next, I'm going to talk about another setting, which is for distributed setting or federated learning setting. Okay, so this is also an interesting problem, right? That attracts a lot of attention in machine learning. So the problem is that consider this scenario, right? So especially for medical image analysis, your data is not collected on one location. Usually collected on multiple locations. Right? If you only use the data at one location, right, the model will be biased, right? So think about for example, patients at the urban area and the rural area, they may have different statistics, right? Right. So if you only use data at one location, it's going to be biased, right? And also, right, if you consider the medical applications, data cannot be shared. You cannot share your data. Right? It's very sensitive. Right? So in this setting, we need to consider so-called federated learning, right? Federated learning, right? So in this federated learning, so the data at different locations just remain at the original location. We don't move the data. Right? And there is a central server to coordinate the different locations to optimize the model. Right? To optimize the model. You can share the model. You can communicate the model instead of communicating the data. Right? So that is our federated learning setting. Okay, but how do we optimize deep AUC problem in the federated learning setting? Okay. So in this year SML paper, we proposed the first work on the federated deep AUC maximization. Right. So right now you still have the min-max problem, but the objective function it is sum average over k components, and each components only access the data defined over the data in that machine, right? So the capital K is the total number of machines, right? And each machine can only access its own data. Okay, so how do we optimize this objective, right, in a distributed fashion in the federated learning setting? Okay, so we proposed a federated algorithm, and this is the algorithm basically running on each local machine. Right? So it's very, very, very simple, right? So these two updates and primal variable, dual variable is just like a stochastic primal dual method. The only difference is that each machine only use the local data. Right? So this ZK only use the data of the case machine. okay, to update the primal variable, to update the dual variable. All right, and then after a number of iterations, so every machine needs to update the model, but we need still communicate the model. We don't want the machine, just do by itself, right? Right, because we want to optimize the single objective, right? So we still need to communicate. So after a number of iterations, so I here is a parameter, right? So after I number of iterations, we're going to communicate. So all the K machines, we're going to average the model, average the primal variable, average the dual variable, and then we'll start the next round. Okay, so this is a federated deep AUC maximization. Very simple, and we prove that under this PO condition. So we prove the iteration complexity and also the communication complexity. Right? So this is our previous paper in the single setting for the AUC deep AUC maximization. And this is the iteration complexity 1 over mu square epsilon. That is what we mentioned before. And the naive parallel version, so you can implement this algorithm in a naive parallel version. So basically each machine compute average stochastic gradients and average all those stochastic gradients to update the model. Right, so with this naive version, so iteration complexity reduced by a K factor, and the communication complexity is the same as the iteration complexity. So for our algorithm, okay, by introducing this I parameter I, okay, so we can prove the same iteration complexity. So right, so it's reduced by a K factor. If you have K machine, reduce by a K factor. But the communication complexity can be dramatically reduced. So right now it's 1 over mu to the power 3 over 2 and epsilon square root of epsilon. Right? It's compared to this one, right? So especially when epsilon and mu is very small, right? So our communication complexity could be much better in a certain range for the K value. So as long as K is less is equal than K is the number of machines, okay? K is less equal than 1 over square root mu times epsilon, right? So our communication complexity would be better, right? So usually mu value and epsilon value will be very small in practice. So we can tolerate a large number of machines. We can enjoy better communication complexity. All right, so that is the federated learning of deep AUC maximization. So before I jump into the next part, is there any question? Okay, great. Okay, so let's move on to the next part, is evaluation, right? Okay, so we want to evaluate our methods on real data. In particular, I want to evaluate on the medical data, right? Because as I said, medical domain, in medical domain, medical analytics, AUC is the most common method, right? to evaluate, to compare different classifiers. Okay, so the first task that we choose is this so-called CheXpert competition, right? So this is a competition organized by the Stanford machine learning group, led by the Professor Andrew Lin, right? It is launched in last year, January, and so far it has attracted over 150 teams globally to attend this competition. Okay, so we entered this competition in the end of May because at that time we just finished a paper on the min-max optimization, and we want to test that. We want to test whether our method can be really useful in practice. Right? So we enter in this competition, and in the end of August we just got the first place in this competition. Right? And so this is our AUC is 0.9305. And so this is the original first place, is now second place, is 0.9299. Right? So one thing I want to mention that so the second place, this method here is actually use domain knowledge. Okay, because right now, let me mention a little bit about the task. So right now, so task is that given an X-ray image, okay, given an X-ray image, you want to predict whether this patient has certain diseases related to the chest, related to the lung, right? For example, pneumonia, right? For example, COVID-19. Of course, COVID-19 is not labeled there because at that time there is no COVID-19, right? So you want to predict a certain diseases. So there are a total of 12 diseases in this data, right? So, all these 12 diseases, they have correlations, right? So the second place here actually utilize the domain knowledge between these diseases. Okay, so our method is purely data driven. Okay, it's simply by maximizing AUC score. Right? It's purely data driven. Right? So this is the AUC score, and the second number, this column here, right? So 2.8 means that. So the organizer also compare your model with the human, with the radiologist, with the experts. Right? So there are total of, so on each testing image, they hire 3 radiologists to label the data. Okay, and then compare your model versus the 3 radiologists. Actually, each image there is a ground truth label. The ground truth label is labeled by 5 radiologists. Okay, so use 5 radiologists as a ground truth label, and now compare the model with other 3 radiologists results. And so here 2.8 means that our model is better than 3.8 over 3 radiologists. Okay, so this is the result. So a little bit about this CheXpert competition. So it contains a big data set with 224,000 X-ray images from 6,500,000 patients. Okay, it's collected from Stanford Hospital, and each image is labeled by one of several of the 14 chest radiographic observations. But the evaluation is only on 5 selected diseases. And so this is decided by the organizer. Probably these 5 diseases are most difficult diseases. All right. Okay, so we got this first place. And then we also did experiments comparing our AUC model and the standard deep learning method. Right. So here, right, so this is we consider different neural network structure. And so this is DenseNet with 121 layers. The base model means we just minimize the empirical error, the average of the surrogate loss, like logistical loss. And this is standard deep learning method. And then on top of that, we maximize AUC. Okay, and then we compare the AUC in each category, in each label here. So on average, we have 1% improvement in each category. Okay, and also no matter is this neural network structure or this neural network structure, so we have average 1% improvement, right? And this is the ensemble result is also 1% improvement. This is the previous best results. Okay. All right, so this is the results on the CheXpert, CheX X-ray image classification. Okay, so second task that we did is the so-called melanoma classification. Okay, and this is also competition. This is a competition at Kaggle. So Kaggle is a website that maintains all different kinds of machine learning competitions, right? So different organizations, different companies can submit the competition, and attract a lot of people to attend this competition. Okay, so this year there is a melanoma classification competition. So it runs between May 27 to August 10. Okay, so this is our results. So we finally we ranked 33 out of 3,000, more than 3,000 teams. Right? So and our AUC is about 0.9438 versus the top 1 AUC. The AUC of the top 1 performer is 0.9490, very close. But I want to see that our model is only, our result is only ensemble of 5 models because we don't have a lot of GPUs. But the top 1 performer used a ensemble of 80 models, right? Using 80 models. So if we use that number of models, we probably can get even better result than this. And you can see that this data is very, very imbalanced, right? So out of 33,000 training images, only 584 are positive examples, and remaining are all negative examples. So it's very, very imbalanced data. Okay, so that's two medical image classification tasks. So next, I'm going to show you some other results on the benchmark data set to evaluate our loss function, our optimization algorithm. Okay, so this is comparing the marginal loss of square loss. So I compare this on the toy example. So we also compare on the real data. So here we choose another image classification data, cat dog data. We classify image into cat and dog, right? And here we control. We add some easy examples, add some noisy examples, and we compare the test accuracy. So x-axis is the number of iterations we optimize. And you see that the new loss, margin-based loss, is much better than the square loss in terms of testing AUC. So this slide shows the compare the convergence speed of different optimization algorithms. Okay, so the blue and the purple curve, basically the best performers here. They are our algorithms exploring the PL condition. PL condition has faster convergence. So the green curve is actually our early algorithm without exploring the PL condition. And you can see that actually exploring the PL condition is faster in practice. And the red algorithm is a standard LGD minimizing standard error rate. So it's not very good for AUC. Okay, so this result here shows the experiments for the federated deep AUC maximization, right? So the result generally result shows that with more machines we can converge faster. Right? So in this figure, so the K, right, is the number of machines. I is the number of iterations. How many iterations we will communicate? So we fix I, we increase the K, right? So you can see that with more K, so the algorithm converge faster. Right? Converge faster. Right, so these two figures showing that we fix K number of machines, okay, and we increase I is the number of iterations between two communication routes, and we want to see that, with how many iterations, right? So how frequently we communicate, whether we sacrifice the performance. So actually, right? So if you compare I equal to 1, which communicate every iteration, right? So we communicate, for example, every 512 iterations, which is a green curve, right? We don't sacrifice performance, but the training time is much reduced. It's much reduced because communication cost is much reduced, right? So this verifies this federated learning algorithm is actually works very well. Okay, so that's all I want to show today. So finally, I want to make a conclusion. So we have proposed margin-based loss for the AUC, which is more robust than the square loss, but also enjoy the same benefit of stochastic optimization. And then we propose a series of stochastic, non-convex, strong concave min-max optimization algorithms with fast rates. And also we proposed communication efficient federated learning algorithm for deep AUC maximization. And we applied our deep AUC methods, right, to the real task CheXpert competition and achieved the first place. But still, there are many open problems, right? For example, how do we prove the consistency of the margin-based loss, right? So in machine learning, in the learning theory, when you propose a new surrogate loss, you want to show that this surrogate loss is good, right? It's good, it's consistent. Consistent means that if you optimize this surrogate loss in the population level, if it is equivalent to minimizing the 0-1 loss in the population level, then it is called consistent, right? So we want our surrogate loss to be consistent, right? So we're trying to prove this margin-based loss is consistent. And on other problems, for example, how do we improve the convergence rate for non-convex min-max optimization, right? Although I said some rates are optimal, but the dependence on some parameters could be still improved in certain scenarios. And also some other type of algorithm, for example, adaptive algorithms for the min-max problems. How can we do that? And for federated learning, how can we further reduce the communication complexity? Right? What is the low bound? Right? So there are many open problems. And of course, we are interested in the application in other medical data sets. Right? So if any of you are interested in any of these problems, so I'm very happy to discuss with you, to collaborate with you. So finally, I want to thank my students joining. He did a lot of experiments, engineerings, and Yan Yan, Zhishuai, Minrui for the theoretical analysis. We also collaborated with my colleague Qi Hanglin and Hassan Rafiq, which is previous students in Iowa. So, and also thank the NS Career Award for supporting this work. So finally, I want to thank you for listening to this 1 hour long talk. So I'm happy to take any questions.